Hi, Lukasz.
Hi, Peter.
Welcome to the podcast Everyday Metallurgy.
Thank you for having me here.
Today, we're going to talk about a theme that we have had before. It's about metal powder manufacturing. But we're going to talk about a very special way to make metal powders that I, in fact, was not aware of until recently. I have been in the metal powder business for 25 years. But I absolutely still have something to learn. So I am very happy to have you with me today to teach me about this new technology. Could you introduce the theme, your background, and how you came to where you are today?
Okay, so my name is Lukasz. I am CEO of Amazement Company, which is basically a spin-off of Warsaw University of Technology. Although we are, no longer a spin-off as there are 60 people there. I also did my PhD at Warsaw University of Technology, working with LPBF, with 3D printing of bulk metallic glasses. And also I am, say, brains behind what we call right now repowder, or what we call, let's say, ultrasonic atomization, which is not my invention. It's actually quite an old tech, but I was, I believe, one of the very first people to kind of reinvent it or bring it from the forgotten times where it was, not really used. So actually, I started working on this topic. That's quite a story, because I wanted to have some powder for my PhD. I was looking for few batches of spherical powder of zirconium, and simply to do alloy development and see which one will be superior, which alloying element could avoid cracking and so. But the troublesome part there was that I had around 50,000 euro grant for 4 years, including my salary. And when I tried to do some atomization, so the first quote I received was 40,000 euro for a single atomization, including elements, casting, bar for AGA, and single atomization with no warranty. So that was a bit obsolete for this R&D purpose. Then I did something strange for a student back then, which is I took an old powder metallurgy handbook. It was Bose 1991, I believe that was the book. And I was screening through different powder manufacturing methods. And there was a small paragraph on ultrasonic atomization. So the paragraph went more or less like, oh, by the way, there is such and such method. People are mostly using that for solders, but there are some reports that high melting point materials were also used, but it's obsolete because it produces very spherical particles, which are not the best ones for sinter and press processes.
Yeah, of course.
Yeah, and it's not as productive as let's say competing methods that somehow won this technical competition back then. So I started digging. It was 2015 or 16 at Warsaw University of Technology. It came out that it is possible to replicate the experiments that people were doing in 60s and 70s, and other technologies progressed since then. It is much easier to use ultrasounds. There are more and more let's say ultrasonic engines, sonotrods, generators available, and we found that. But the most important point is that back then it wasn't so needed to have small quantities of spherical powders, while it was exactly my goal to have myself a setup to create multiple alloys for my PhD. And long story short, this is how this history started. Since then I'm working mostly around 3D printing and ultrasonic metal atomization.
Yeah. I ask you to give me some insight in what is this ultrasonic atomization, and you shared some very old papers with me, and I was amazed that it was something that happened far back, and but at that time they were only able to do it on very low melting alloys due to the ultrasonic head and some of the materials. There were a lot of wear on the parts due to the liquid metal and the ultrasonic vibration.
So ultrasonic atomization is much easier when we're dealing with low melting point metals. Mostly it is right now routinely used in solder production, to create powders which are a substrate for solder pastes. So there it's widespread. But even in 60s and 70s, people were experimenting with titanium, with nickel, but those were very small setups, and again that wasn't as productive as people were already getting with gas atomization. That's why this technology lost. But there are papers, from for example, and patents from Heraeus. They did in 1980s, for example, titanium atomization. But again, those projects were stopped as let's say tools used back then were inferior. But right now, besides what we do, this technology is used mostly for solders. And for example, in China, there are multiple companies doing atomizers for tin bismuth lead systems. Exactly. I can also show, to make it easier, I will share my screen to show you how this technology actually looks like.
Yes, that would be nice, because I think people are now getting confused. How do you make powder with ultrasound? That's very strange to understand.
So before I share my screen, I will give my favorite example. So as say, people are familiar with gas atomization. It's basically spraying. So in ultrasonic atomization, we have something more or less like a mist, like an ultrasonic humidifier. We pour water, we apply ultrasounds, and then droplets are generated. So the closest life example, and then real life example, is ultrasonic humidifier, and the mist actually are fine droplets. Right now, I will show you the movie from one of our papers that is recorded with high-speed camera. So at the bottom, you can see plate that is agitated with ultrasounds. So on the top, there is liquid film. In this case, it's just water. But you can see at certain amplitude, when we reach certain threshold, there are droplets ejected from the melt, from the liquid. But in here we can observe a few interesting parts. The first one is that most of the droplets are similar in size. So that is one of the perks of ultrasonic atomization. It's very easy to get almost mono-sized particles. So if the process is fine-tuned the right way, the particle size distribution is extremely narrow. And the other thing that you can observe here is that the liquid have to wet the surface of the vibrating element. Otherwise, if there is no wetting effect, there is simply ultrasounds cannot be transferred, and controlling.
If it's only a spot.
Yeah. And
you need a bigger surface.
Yes, and then the droplets are just bouncing on the plate. And controlling the wettability is one of the critical things that are important for the process. But this is how it looks like with with water. And yet another example, when a droplet hits the vibrating plate, you can observe right now in the cavitational mode, there is this quite intense effect of atomization. But here we can observe that there are both large and small particles. And this is due to increased amplitude where we went to so-called cavitational regime. So when there is a high amplitude of ultrasounds, at certain point there are voids, bubbles formed in the liquid, and when they collapse, it's kind of a micro explosion, and this micro explosion widens the particle size distribution. So, and and this is how it looks like. This is how it looks like with metals. I'm trying to show the video. So on the left, you can observe there are droplets falling onto this vibrating plate. And this plate is not water cooled, it is simply agitated with ultrasounds. And the comet tail on the right is, those are actually particles while they're solidifying. But the problem with the left setup is that if the plate is not water cooled, it is subject to extreme fatigue, extreme conditions. So within
a lot of wear, I guess.
Wear, fatigue, those plates, it's like 1 million cycles of fatigue below 1 minute. The temperature of molten copper or steel, there are very few materials that can withstand it. So if we were dealing with something with higher melting point, then we have to water cool the setup, and that is the one on the right. But then instead of pouring the liquid, we are directly melting material on top of this vibrating element. So you can see
the rod you melt off.
Yes. So the rod right now is, as you can see, consumed as it's being molten, because as soon as it's molten, the vibrations just eject droplets. So this is the one that we use mostly for refractories. So those are the, let's say, two basic approaches for making metallic powders afterwards. The induction, or the one where the tools, sonotrodes, are not water cooled, is mostly used for low melting point materials, while the refractory ones require certain cooling. Otherwise, it will just disintegrate.
Yeah. What is the atmosphere in the chamber while you do this?
That is actually a pretty nice question, because it could be actually anything. Usually we use just inert argon just to keep it from oxidation. But as there is no direct consumption of gas in this process, unlike for example gas atomization, we can use any gas. Sometimes it makes sense, for example, to use helium to speed up cooling of the particles. Sometimes we can use reactive gases. For example, we used to run experiments where we used a bit of methane just to introduce carbon into particles as they are produced. We used to also work with hydrogen. There was an idea to in situ reduce powders, so to reduce the oxygen content in the melt, just to get it solidify in hydrogen. It works for some alloys, but for example, for titanium it doesn't. But for steel or Inconels, it works pretty easily.
Yes. And for the liquid one, there's be some parameters like superheat. So how hot is the melt above liquidus?
Yeah, that is for the induction method, higher the better. So that is the general rule. Higher the overheat, it's easier. Usually for copper, we try to keep it around 100 to 150 degrees above liquidus temperature. So that's quite an overheat. Sometimes if the metal is not flowing well, for example, we used to run experiments with not melt directly, but with kind of a slurry. So to create metal matrix composites, we atomize slurry with aluminum and silicon carbide, and then making this slurry flow through orifice in a crucible. It required a lot of overheat, not really typical for aluminum. But let's say 100 to 150 degrees is typical. Because we have to heat the plate, that is to avoid freezing on the plate, and B, that the higher the temperature, usually the wetting effect is easier, is better.
Yeah. In normal atomization, you often get we talked particle size distribution that could vary a lot. But you also get satellite formation when smaller particles collide with larger particles. Is this the same? Do you also create defects like that in ultrasonic atomization, or is it different?
Actually, it's much different because when you consider velocity of the particle in ultrasonic atomization, it's in order of 20 centimeters per second. That is fraction of fraction was in gas atomization. So
yeah, absolutely,
so the particles really solidify. It's like a mist. So there are very few chances for the particles to collide with each other. Now, getting satellites is pretty hard for us, and in general, getting fines is hard. It's very hard to get any particles below 20 micro, for example. So in case of sometimes it's advantage, sometimes it's a disadvantage. But in case of ultrasonic atomization, it is very tricky to get particles fine enough to become satellites. That is one point. And the other one is that low velocity, the mist behavior is gentle or on the droplet. So we have so-called book of powders with several dozens of SEMs of different alloying systems, and defects of this kind are non-existent. There are other ones. For example, it is possible to partially evaporate particle if we're talking about this plasma-based method. So when the particle is traveling through plasma and taking into account that it is quite a time, due to low velocity, the particle is overheated there. So for example, if we're processing zinc or manganese containing alloys within this plasma setup, those particles overheat and part of those volatile elements can evaporate. So this is kind of a defect that is observable there. That in terms of sphericity, it's quite boring. It's very hard to get non-spherical particles.
Yeah.
Unless
it looks very spherical.
And it goes and goes and goes. There are very few systems that produces non-spherical particles. But for example, bismuth and silicon, they produce particles which are kind of an octagon. So they look like a crystal, but not due to some interaction between particles. But when they crystallize, you can see the crystal just break the internal forces of droplet, and then you have like those small octaedons, shapes in your powder. That is something that we observe for silicon, for germanium. But besides that, it's it's very hard to get satellites.
So those particles, even though they are, are we typically around 20, 50 microns?
Yeah, 50, usually I will show you the particle size distribution, because as for PSD, that is my favorite one. So the PSD, if we are in, let's say, low or medium level amplitude. It's pretty narrow, and it changes with frequency. Basically, higher the frequency, finer the particles will be. But as you can see, there is almost nothing below 20 micro, because then the frequency would have to be extremely high. And getting high frequency is hard because maximum available power of ultrasounds scales with power 3, 1 divided by power 3 of frequency. So if we have, for example, 4 kilowatts available in 20 kilohertz, then 40 kilohertz will be like below 1 kilowatt. 60 kilohertz is like 500 watts, and higher frequencies have lower and lower power, and it's much easier to contain it in the system.
So the big area for this, as I see it, could be the fluidizing abilities when going for 3D printing.
And that is actually, I would say, 80% of what we do currently. So that is why this project started back then at Warsaw University of Technology, just to bring multiple alloys for LPBF tech, and it's pretty handy. Right now we treat it mostly as a handy tool to do some alloy screening. It is possible to use as a production tool, but then there are certain limitations applied. For example, it doesn't make any sense to atomize steel. It is too cheap and it's too hard to atomize, but it makes sense to use it, for example, for, of course, solders, which is known, but for aluminum and titanium, it also makes sense to use it as a production tool. We have one of our customers using it in US for creating powders for radiopharmaceuticals. So he creates powders out of novel certain elements to be inserted into a nuclear reactor to go through certain transmutation, and then certain drugs are produced with those. So those are minor applications for us, but
I could see a potential, because when you show that the small rod, typically when you want to make atomizing powders, there's a minimum amount. A melt bath could be 5 liters. So you minimum have to put in 10 to 20 kilos. But in your application, you could take a very little piece,
the smallest,
and put it in and just make a few grams.
And even 500 milligrams. That was the smallest sample we did. Then it's harder to find the powder than to atomize it. But there are certain applications where you're not really looking into powder as a powder, but particles. I will not name those applications, but there are certain, let's say, products where a single particle is actually an end product for the customer, and very tricky alloys or elements are used, like iridium, osmium. We have some non-3D printing application where beryllium is used, and this particle is part of some sci-fi detector, and then making small quantities is of use.
Just interrupting to talk about how to make metal powders from these alloys. You can see here behind me that these yellow colored, they are called refractory metals, and the melting points are very high. Tungsten 3422 degrees C, tantalum 3070. So it's pretty difficult, and if you should do that in a traditional melt puddle, you should have a refractory material that could hold this inside and not melting. But as tungsten is the material in the world with the highest melting point, how should you keep that into a pot if everything else around it melts before it melts? So this method could be the solution to make powder for this kind of materials. Yeah. It sounds pretty smart. And those alloys, they go to pretty high temperatures. How high can you go? You started back in the old days with soldering material 250, 350 degrees C. But where are you today? Titanium is 1500 liquid level, but those last one you said, they are pretty high in temperature.
So routinely we were doing niobium alloys, which are around 2,500 degrees Celsius. Those are pretty easy to be atomized. We have some, let's say, single experiment. We have, for example, experiments with rhenium, which is over 3,000 degrees, and multiple alloys, high entropy refractory alloys also around it. Hard to be atomized is pure tungsten and pure tantalum, and it's not even hard to atomize, but it's hard to feed it, carefully enough to be able to melt it, and quite decent superheat. Because, for example, we did pure tungsten, but then it required a very fine wire as a feedstock to be atomized. Otherwise, when we have a blob of tungsten, then atomizing that is almost impossible. But recently we did some announcements with also laser-assisted ultrasonic atomization. So there, instead of a plasma torch, we are using high-power laser, and that is exactly intended for for pure tungsten, tantalum, and those refractories.
Yeah, it sounds crazy. I would have asked about the material you put on your ultrasonic head, but it doesn't really matter when you do it this way. Or do you still see wear when you work with these materials? How do you connect the ultrasonic head with the material?
So that is that is the most tricky technological challenge, because you have to consider the sonotrode, the head, as an element with steady heat flow. So it's heated on the one part, lower part is heated cooled with water, and the upper part is usually connected there are several different ways. It could be braced, it could be diffusion bonded, it could be just sintered as a single piece. But the best case scenario, when it's possible, is to atomize same material on same material. For example, it is possible to agitate ultrasonic head out of titanium, and then when you're melting titanium as a feedstock directly and atomizing titanium directly, there is not it's not possible to contaminate anything. It is possible
that's an advantage.
But some materials are impossible to be vibrated because they exhibit extreme losses, mechanical losses. So then it is necessary to either connect them or to use some intermediate material. For example, dealing with titanium, it is also possible to use molybdenum as a ultrasonic head, knowing that there could be some contamination if you overheat the melt. Or if you're processing, for example, steels, you can process it on top of tungsten, and then due to high melting point of tungsten, there is no contamination. But you have to connect tungsten with something else to make it vibrate.
I think the first time I looked at this, I said, "Wow, that's very interesting. I might be interested in using it." So I looked at an application where I would need something like 5 to 10 tons. But yeah. How do you see scaling potential of this? How large volumes could you go to?
That is the only honest question is honest answer is it depends. So we are having one setup where the molten metal flow rate is around 20 something kg per hour, but it applies to aluminum. So that is something to run continuously, and then scaling of setup is rather to have multiple modules with single ultrasonic head instead of scaling the single setup up, because there are certain, let's say, physical limitations. In case of titanium, something around 1.5 kg per hour is doable, which is not ultra large scale, but if we compare it to size and let's say costs of gas atomization, then it looks a bit differently, because I always say that within a single room where AGA is working, I can place 20 ultrasonic atomizers, and their cost would be, more or less comparable to single AGA. So it's hard to, compare one gas atomizer, which is 1.5, 2 million euro investment, to ultrasonic atomizer with, of course, lower throughput, but it's a bit different approach. What we are doing is rather trying to press most out of a single unit, but with those limitations, it's easier to add additional heads to get higher throughput.
Yeah. I like this idea of, instead of having one big, to have multiple. It also gives you a kind of flexibility that is difficult to have.
I used to clean one's gas atomizer, and I wouldn't like to do it again. In our case, it's much easier, and sometimes we are switching alloys several times a day in a single unit. So if there is a campaign of several nickel alloys, with small chemical differences, then it's doable. In gas atomization, I wouldn't dare.
No, it can be a mess. Then it's also today very modern to talk about sustainability, energy consumption. How is this compared to other ways of producing powders?
So that is a nice question, because actually yesterday I've been doing some additional calculations on aluminum alloys. If we compare it with gas atomization, there are, let's say, several places where energy is wasted. In both cases, we have to melt the alloy, and that is something that is impossible to avoid. So let's keep it as a constant in both cases. But ultrasonic atomization uses almost no gas. So I can, let's say, I can just use a single tank for a few days as for welding, while same tank would disappear within half a second in gas atomization. So energy, let's say, consumption in terms of energy consumption is superior, but it mostly is considered if we're considering compressed gas. That is energy to compress it, purify it, purchase it, and so and so. So this is where certain advantages are present. For example, if you see this vibrating plate, even when we have a pouring rate of 25, 30 kg per hour, the consumption of energy of those ultrasounds are like 100 watts. It is almost nothing. So that is so consumption of ultrasonic energy is we can that is fraction of what is used for melting. And in there, if you consider this one, in my opinion, and if we exclude melting, or we say that everybody have to melt the material, then we can say that it's the most efficient powder making technology. But that comes with certain scale.
Yeah, you have to melt it.
But we have to melt it. Yeah.
Lukasz, I'm also curious. It's a pretty new company. So the learning curve and the growth must still be pretty steep. So where do you see this technology in 10 years from now?
So my opinion is as follows. We are right now mostly using it as a tool. I think in 10 years that will be a standard tool for those who are developing new applications, new materials in additive manufacturing. So if there is a material science department at the University ABC, and they are working with LPBF, DED, there will be also sooner or later some kind of atomizer. Most likely ultrasonic one, because it's much easier to place it in existing lab instead of building a building. So that is one point, and I think that we are already getting there, because when we're talking with our customers, partners, with an additive manufacturing, let's say industry and academia, that is already kind of a state of the art. But I believe that with ultrasonic technology, there will be certain materials where this technology is or will be competitive to gas atomization. And I'm talking mostly about aluminum and titanium. In case of titanium, because we have to compare it to AGA, and then both yield isn't as great as in closed coupled gas atomizers, and they're providing that we can get 90% of powder within LPBF particle size distribution, then there are certain benefits with, let's say, expensive materials. Titanium, niobium, basically refractory and expensive materials. On the other hand, it is very easy for us to atomize aluminum, magnesium on large scale, and I'm talking about dozens of kg per hour. So I believe that in next 10 years it will be still an R&D tool in academia, but it will also find its niche, the niche that was not found those 40 years ago in terms of titanium and aluminum alloys.
Fantastic.
And B is that we are right now finding actually a new applications. Recently, we got a call with a customer doing zinc for batteries, for example. So for me, right now, exploring where metallic powders could be used, but outside of additive manufacturing, lithium powder, zinc powder, magnesium powder for batteries, fuel cells. That is something that is very, very interesting for us, and I believe that those industries that could pay for kind of a premium ultra-spherical powders, not necessarily in additive, but energy storage, so will drive this technology in the future.
Yeah, and you also shortly talked about this in situ reaction with the gas, where you can, while you atomize, produce specific materials with this in situ gas reaction. Will that grow too?
So initially that was an error, because we started atomizing without inert gas. So just by chance, we looked on SEM how does this particle look like, and one of our partners thought that it's interesting to create kind of a core in a shell particle. So inside it was a pretty ductile titanium, but he wanted to have titanium nitrides outside to use it for some thermal spray application. He explained it to me that it is like an egg with a hard shell and soft yolk. So when you hit it on the wall, this shell should, kind of go around it. So his intention was to create kind of a layered structure with those core in the shell particles.
Yeah. Wow. I could also see a potential in ODS, so oxygen dispersive materials, to strengthen the material. It is used in some application for high temperature materials, so in the refractory world. So that could also be a potential.
Yeah.
To have a bad sealed chamber.
Yes, we have one project of this kind, and basically, ultrasounds we are using ultrasounds not only for atomization. We are using those right now with several applications that involve liquid metals, and one of those is also quite, let's say, known in the literature, but mostly in academia, is to disperse ceramic particles within molten matrix of different alloys. Usually we're using that for aluminum with silicon carbide, with boron, with titanium boride, to introduce ceramics inside, shake it to the level that we have it uniformly dispersed. But it's also possible with steel. We did, if, let's say, reinforcement content is low enough, it is possible to atomize such ODS steel. If the content of the reinforcement is too high, then it's getting slurry, and it's hard to, it's not behaving as liquid anymore. But it is possible. Yeah, exactly.
Yeah. Lukasz, if people want to learn more about this, where should they go? Could they contact you? Your homepage? Should they go to conferences?
The best case scenario, you can always, contact me. I am still with very deep academic background. We have a few papers published on ultrasonic atomization. So if you go on, let's say, Elsevier or Science Direct and find my name and ultrasonic atomization, there are several papers published on that, with mechanisms, with what could be achieved with this tech. Of course, we have very nice materials on our website, amazemet.com. There are also links to all of those papers included, so you can find it all also there. We are always at Formnext and several other, let's say, additive manufacturing trade shows and conferences. Usually at the TMS and other material science conference, we're also present there. And as a final remark, I could say that if there is project that is interesting, for example, I just invented a new alloy and I wish to get it pulverized, or would it make sense to add ultrasounds to molten, I don't know, germanium to change its grain structure? We have quite an extensive R&D. I mean, we are R&D team, so feel free to contact me. So we might just get involved because we like interesting projects.
Fantastic. Thank you very much. I really enjoyed the conversation. I learned a lot. I loved the video you showed with the mist. I think the water was the most beautiful, but maybe the refractory was the most useful of it. So thank you very much.
Thank you.